you look at the lab and you're reading ahead and the lab says, hey, we're going to be using chemicals or glass or something like that, then you're going to want to make sure you've got the right shoes and whatever on. But
where's my change?
Right in there. Did you need me, James?
Yeah.
What's up, my friend?
If we weren't able to do all the little boxes on the lab,
That's
that's
fine.
fine.
Absolutely. Yeah.
Anybody upstairs? Oh, you
See them all? There you go.
You missed one. What? I missed one? Yes. What do you know? I missed one. I only got 3.
Yeah, we didn't like it with fun because like they put us like oh, more than 10 seconds.
Me. Everybody has different. I've heard 2 as well.
2 makes more sense.
Yeah, depending on, well, if you're in a public place, it's like a half a second rule, but you know. All right, so this is our last lesson for Unit 2. You have your Unit 2 test this week. That test went live 1 minute ago. Okay, it goes live at noon on the day that I issue it. Now, listen up. That test is on Teacheries. It will shut down at 8 a.m. next Tuesday. If you have not completed the test by 8 a.m. next Tuesday, you're not going to be able to. It's going to kick you out. Boom. And it will also shut down after 1 hour. Okay, you have 1 hour to take it. So you log in, you have 1 hour to take your test. Now, if something happens and you go wandering away from your computer because, I don't know, you want to go take a break and it's longer than an hour, you're going to lose your chance to complete it. Okay, so you have a 1 hour window. It's open now. It will shut down on 8 a.m. Tuesday. So don't open it. Don't open it until you're ready to start. Okay, you don't want to open it early and then be like, whoops, I wasn't ready. At the end of this, there's a slide that shows you what your topics are for this test to study. It's also available in your Dropbox, in your resources folder. There is a unit test study topic file in there, and it'll show you exactly what topics are covered. I don't throw out questions that I don't mention, except for those that are always questions, like what's a hypothesis, why is science never settled? Those may show up from time to time, but this will be entirely what's in this unit, and it'll tell you exactly what to study. Okey-doke? So this is our last little bit on space today. So we're exploring our different models. So what do you call a model that is Earth-centered? Okay, Asher. Geocentric. Geo meaning Earth, Earth at the center. Oh, do you need paper? Drew, where'd the paper towels go? Help. Thank you. Jordan needs paper towels. So geocentric model. And this was for many years the acceptable model, right? And then we have sun-centered, which is Piper? Heliocentric, right. So heliocentric is our sun-centered solar system. Now, there have been questions for years and years about whether the Earth or the sun were the center of the universe versus the solar system. Those are different. So our planetary orbits, the flat plane containing all these orbits is, Caitlin. Yes, it's an elliptical plane. What is the shape of an ellipse, Caitlin? Do you know what an ellipse is? Yeah, it's kind of like an oval as opposed to a circle, right? There you go, NASCAR track. Also at the gym, they have those elliptical machines. They're like the walking machines, but your feet kind of make this oval pattern as you go. All right, so how do we figure out the Earth goes around the sun? We did not know this. Oh, there we go.
You, me, every single thing on this planet, we're all zooming through space right now, orbiting the sun at an average speed of 107,000 kilometers an hour. We're rotating while we're doing it. The sun, moon, planets, and stars all look like they're moving through the sky, right? So it's easy to imagine that we're staying put while they all move around us. as long as you don't look too close, which is why the whole idea that the Earth orbits the sun wasn't really accepted until a few hundred years ago, and it took a lot of convincing. A lot of the old geocentric model, where Earth's at the center of everything, was based on ideas developed by ancient Greek philosophers Aristotle and Ptolemy. They explained that the Earth stayed put at the center of everything, and anything we can see in the sky, the sun, the moon, stars, planets, everything, orbited it in perfect circles. But that didn't explain why planets, which at the time referred to anything that looked different from the background stars, including the sun and the moon, sometimes changed brightness or occasionally looked like they were moving in a completely different direction. So the geocentric model tried to explain them using epicycles. These are imaginary points that were moving in imaginary circles with planets orbiting around those points. And it sort of works, though eventually they had to draw more circles around the circles to explain some things and have the planets move faster or slower at certain points in their orbit. Diagrams of the sky were kind of a mess. There were at least a couple of Greek philosophers who disagreed, and the geocentric model was questioned by Muslim scholars since at least the 10th century. But for a long time, especially among Western civilizations, it was just accepted. Everything revolved around the Earth, even if it was hard to explain something. At least until Copernicus came along. Nicolaus Copernicus was a well-known Renaissance thinker who spent the last few decades of his life developing a heliocentric model, where the sun is the center of the universe, which he published just before he died. And okay, we know that the sun isn't the center of the universe, but it was a lot closer to the truth. Copernicus realized that the math was a little simpler if you just had Mercury, Venus, Earth, Mars, Jupiter, and Saturn, the only planets we knew about at the time, orbiting the sun with the moon orbiting the Earth. He used epicycles too, but all the planets in his model get the same speed throughout their orbits, which is what you'd expect if the orbit is a circle. But it was still hard to prove that the heliocentric model was more accurate. For one thing, even if they made things simpler, those circular orbits in Copernicus's universe were wrong. And it was just as bad as the geocentric model for predicting how the planets would move. Then in the early 1600s, Johannes Kepler realized that orbits didn't have to be circles. And if he assumed that they were ellipses, the math fit the motion of the planets, sun, and moon a lot better using the heliocentric model. Around the same time, Galileo Galilei's telescope made things even more convincing, mostly thanks to Jupiter and Venus. When Galileo pointed his telescope at Jupiter, he was able to see its 4 biggest moons: Ganymede, Callisto, Io, and Europa. They were pretty concrete proof that not everything in the sky was orbiting Earth. Then he noticed something weird about Venus. It goes through phases, just like our moon does, from new to full and back, but it's much bigger when it's new than when it's full. That made no sense in the geocentric model, which predicted that sometimes Venus would be closer to Earth when it was new, but sometimes it would be closer when it was full. In the heliocentric model, though, the sun, Venus, and Earth lined up so that Venus would be closer to Earth when it was new. Even with all this evidence, it took a long time for the heliocentric model to be accepted. The church banned heliocentric work until 1758. These days, we know that the heliocentric model wasn't exactly right either. The sun isn't at the center of the universe. There's a lot more out there. And if you want to get technical about it, both Earth and the sun orbit the same point, the center of mass of the solar system, which is just the center point of all the objects in it, based on their mass and how far they are from each other. Since the sun has 99.87% of all the mass in the solar system, the center of mass is pretty close to the center of the sun, but it does move around a bit, depending on where it's to the top or so what,
Hello.
Peter's model is wrong. It's a concept, so many people up there, and we've seen it for ourselves. Thanks for watching this episode of SciShow Space, which is
Right, so if you handed in lesson 3, but I didn't hand it back, raise your hand. Who wants to claim this one with no name? Is that you? Is this one you? Somebody.
That one is not.
Not? Okay. Not Asher. Whose is it? Somebody needs a grade. Liam, you want to say? Is that you? It's always one of these. It's fun. I figured out 2 by process of elimination last week from the junior class. Okay, so if you turned one in, you didn't get it back, and you don't have a grade in your teacheries, it's because I don't know who you are. Okay, so solar system. We're breezing through it because, you know, this is our last bit on the contextual Earth and space stuff before we really hit all of our forces in motion business that is the heart of physical science. So let's see. So components of our solar system. So it has a sun, planets, their moons, a bunch of other small things, and they revolve in the same plane around the sun. So how do we measure the distance of an object from the sun, Bailey? There you go. Astronomical units, or we call them AU. Okay. And this is, you can use other stuff. In a minute, you're going to see it done in kilometers. And that's just the numbers are huge, right? So we can use an AU to kind of help measure because it's just a different unit. You can use anything to measure as long as it's consistent, right? You can use your shoe if you're using the same shoe every time. It doesn't matter. So exploring the solar system. Modern technology includes complex telescopes, piloted spacecraft, probes, and we've been able to travel to all these places that you learned about today in lab. So our traveling to the moon, what were those missions called? Yusuf? These are our Apollo missions, right? Okay. So our Apollo missions went to the moon, and you guys saw a lot of that just in lab. If you want to see an excellent movie that I would love to show, but it kind of pushes the line of appropriateness for the juniors, so I don't show it. The movie that we watch at, like I said, at Christmas is October Sky. That one doesn't push the limit. So The Right Stuff is an absolutely fabulous movie. It talks about basically the steps we took to get humans into space and to the moon, but mostly just getting them into space. One of the first things was building a vehicle that could break the sound barrier. Does anybody know the name of the man who broke the sound barrier? Do you know? Do you know?
Chuck Yeager.
Chuck Yeager. You got it. Yep. And Chuck Yeager. And so this movie starts with like Chuck Yeager breaking the sound barrier, but it goes through, you know, Alan Shepard and this whole crew of first guys, and the kind of tests and stuff that NASA did with them were interesting because they really didn't know what effect space would have on them physiologically. So they tested everything, and I do mean everything. So they made sure that the astronauts came back functioning fully. So they did all the tests. It's interesting. So these were the Apollo missions. So we've had more recent missions. They tend to be more near Earth. We're putting humans up into ISS. So what is an unpiloted vehicle that carries instruments called, Ridley? That's right. Okay, so these are our probes. They don't have people in them. We send them out to get information, and they can transmit it back. Like I said, Voyager is still talking to us, which is insane. Hey, Alexa, where is Voyager 1 today? If it knows.
Sorry, I don't have an answer for that.
Okay, it's way out, past Kuiper Belt, way out. So we've got our moon, and it is missing something that allows the surface temperature to really vary. Milo? Yeah, we talked last week about how our atmosphere is important so that we can maintain a relatively steady temperature. I know it doesn't seem steady when we go from 100 degrees to 32 degrees Fahrenheit. Like, that's crazy, but it's steady compared to some other planets that have massive changes between their day and night. I mean, we're talking hundreds and thousands of degrees between their day and night. So, you know, the fact that we've got, you know, a couple degrees below zero or whatever, and then a couple degrees over 100 Fahrenheit is not that bad. This is pretty stable. So we have surface features on the moon. So what are the flat, low plains called? Yes. Maria, that's right. Okay, and it's correct. Did you say it Maria, not Maria? And this is another word with a root in it. M-A-R tends to deal with sea. Marine, right? Okay, next one. The mountains are highlands. Okay, highlands. And then these round depressions caused by impacts are, Emily? Craters. Okay, so there we go. And then the rocks that travel through space. Liam. Okay, yeah. So this is one of those ones where it's weird. You've got meteoroid is the rock itself, right? When it hits the ground, it's a meteorite. You can pick it up. The rock on the ground is a meteorite. The phenomenon of the rock moving through space and leaving that big trail of light is the meteor. So it's three different things, but it's all the same thing, but not the same thing. It's like the trinity of meteoroid, meteorite. Yeah, it's a space rock. The whole phenomenon of it, when you see it moving, is the meteor, but it's the meteoroid moving that's causing the phenomenon, and then that's a meteorite when it hits the ground. Isn't that fun? So scientists hypothesize the moon formed after an enormous collision in early Earth history. And we think this because the moon is composed of relatively similar, it's relatively similar to that of our terrestrial planet here. A lot of the same stuff can be found there. So we think it broke off of Earth. Earth got slammed into and a chunk fell off, basically, and became our moon. So what do we call these different, okay, Jordan. Phases or shapes of the moon. Yep. Okay. So these phases, the moon's phases are caused by changes in relative positions of the Earth and the sun as it revolves. All right. So then we have, yeah.
There's typo in the top right there.
Yeah.
It says different shapes of the moon.
I think somebody caught that one, but yeah, good call. All right. So eclipses. All right. Xander, was your hand up? Oh, no, it wasn't. Okay. All right. Go for it, Colin.
Eclipses.
Yeah, eclipses. That's an easy one. See, y'all were like, not what? For real? All right, so eclipses, solar eclipse. Who saw the last full eclipse in totality? Who got to see it? Yeah? Does anybody know when the next one is? That'll be coming across the US? It's April. Yep, it's during this school year. It's like April 9, something like that. It's not going to go over Georgia. It's going to come up through Mexico, go over like Texas, kind of, I think, make its way through like Illinois, Ohio, an edge of the lakes, and on into Canada. And I'm jealous because dead center totality is Waco. So Cole at Baylor and everybody at Baylor will be able to step outside and get perfect totality. They are dead center. It's absolutely the perfect spot to be. By the way, if you want to go see it, hotel rooms and Airbnbs are running several thousand per night because people aren't stupid and they know you want to come real bad. So they can charge what they want. There's your market at work. So it's the last one for a while. I think 20 years or something. It's I think. But anyway, it's expensive. So I mean, we looked, we're like, oh, we'll get an Airbnb. Oh, look at that little 2-bedroom house for $8,000 a night. It's crazy. We did, however, find if you're looking for a way to do it, rent an RV. It's probably going to be your best way to get there. We may do that because we'd like to go, but geez. There's no way Waco is booked already. There's no way we can stay there. So, solar eclipse is when what casts a shadow on what? Asher. Yep.
The Earth casts a shadow on the moon.
Yeah, the moon casts a shadow. Okay, yes. Earth, yeah. That's backwards. This is backwards, but you said it right. Yeah, this is written backwards, but you said it right. I need to fix that. So what do we call the shadow? Okay, Yusuf. No, the shadow. What do we call the shadow that it makes? Do we know? Hi, Chloe. The umbra. Yeah, and then the less dark area around it is the Jordan penumbra. Yeah, oh, that's exciting. Umbra and penumbra. And the lunar eclipse occurs when what shadows what, Colin?
The Earth casts a shadow on the moon.
There you go. Earth casts a shadow on the moon. This has to be like kind of there. It's weird. All right, so tides on Earth. All right, we talked about this a little bit, but tides are your regular rise and fall of ocean water, and really, any of the water that like brackish water that kind of leaks in areas around like the deltas, stuff like that. You can see the tide effect there. So they're caused mainly by differences in the moon's gravitational pull on Earth. So you have a spring tide. And this is the change between high and low tides is go ahead, Xander. Wait. Yeah, I'm sorry, Lucas. Yes. Lucas, Xander. I said Xander, and then I'm looking at you both and I'm like, y'all are, yeah. The rightest and the greatest. You got it. Okay, so the neap tide is when it is okay, Xander had that one. Lucas, do you have this one? Yeah, the least or the smallest. You got it. Okay, so there we go. All right, now, these are our phases. What do we call it when it's getting more towards full? What do we call these? Which one is it, waxing or waning? Waxing is when it's getting more full, and waning. So this is going from a new moon to the full moon is waxing. And when it goes from a full moon to no moon or new moon, that's waning, right? All right. Now let's talk for a bit about our terrestrial planets. So these are the ones that are similar to Earth, and these are your 4 inner planets, so closest to the sun. They're dense, they're rocky. So we got Mercury, Venus, Earth, and Mars. Okay, so now we get to have a little fun. Mercury, we have some data here on Mercury, but I don't have the year length in Earth days. Does anybody want to guess? Jordan, do you want to guess?
I found a browning point.
What'd you find?
It says in the binder, neap tide, it changed between a high and low is.
Oh, you got one. Okay, good. That's one. Good deal. All right. Does anybody do you want to take a guess at this, Jordan? What this might be? Oh, I bumped it. I'm sorry. I've actually bumped it by accident. So almost 88 Earth days for 1 year on Mercury. All right. So here's Venus. Anybody want to give us a guess on a day length? Colin?
360.
360. Want to take a second guess, Liam?
60.
60. All right. Let's see. 243 Earth days to have 1 day on Venus. So what does that tell you about Venus's rotation? Piper? Is it rotating more quickly or more slowly? What do you think?
It takes longer to go around the sun than itself.
Right, but it's day. So an Earth day, it takes 243 days on Earth for there to be 1 day on Venus. So not going so not revolving, but rotating. What do you think? What do you think it means, Drew?
Oh.
Slower?
Day is almost once its year.
Yeah. Yes, they do. So yes, it's slower, much slower, right? Much slower. One rotation of Venus, almost a whole year on Earth has gone by, and almost a whole year on Venus. So Venus's year is like a day and a piece of a day. That's the whole year. That's kind of weird, right? All right, so Earth, what's our radius? Anybody want to guess? Xander, did you want to guess? No? Look, no. Okay. Yusuf? Xander, do you want to guess?
Like 10,000 miles or something.
10,000 miles? 6,400 kilometers roughly to the center of the Earth. That's being measured from sea level. So yeah. And then we have our 1 moon, right? Oh, look. And look at our day length here. 23.9, not quite 24. And look at this. Okay, how do we account for this, Bailey? That's our leap year.
Yes, that.
What date gets added to the calendar? February 29th. If your birthday was on February 29th, what would you do?
Celebrate either the day.
Technically, you're only like a quarter of your.
Isn't that weird? Yeah, that would be odd, but yes. There you go. So you'd have to pick a day, right? Lucas?
Man, you could like celebrate it. You could celebrate on the day before, but then when it's on the leap year, you can celebrate both.
Oh, that would be fun.
Yeah,
Yep.
2 years in 1 year.
All right, so Mars. Okay, how many moons does Mars have? Oh, Liam, yes.
2.
Liam says 2. Let's see. Liam is right. Boom, excellent job. All right, next up, we're going to move a little further through our solar system. So our inner solar system, we're still there. Now we're talking about our asteroid belt, right? So we got Sun, Mercury, Venus, Earth, Mars, asteroid belt, right? And scientists hypothesize that these are remnants of an early solar system that never came together. So they're just kind of floating around out there, banging into each other and whatnot. So we get through our asteroid belt, and now we're at our gas giants. So these, what are they mostly composed of, these outer planets? Piper? Hydrogen and helium, yes. Okay. Liquid hydrogen and helium mainly. All right, so Jupiter, right? Saturn and Uranus and Neptune. And then we have Pluto that's not really a planet anymore. We downgraded Pluto in a while ago. Yeah, we downgraded Pluto. It's, yeah, I think around 2007 or 2008, I think we downgraded Pluto. It's now a dwarf planet. It's in the same category as Eris, which is similarly sized and in the same plane. Now, for like the couple years that my kids were in public school, Cole actually gave a book to the librarian at his elementary school because it talked about Pluto being a planet, and he handed it in and he's like, this is no longer accurate. It needs to leave your library. So way to go. All right. There we go. Lucas.
It was in 2006.
Okay, 2006. There you go. I had a good guess for 2007. And then we have our comets. Comets, these are these dusty, you can think of them as dirty snowballs, right? And they're flying around. When I was a kid, the big one to come through was Halley's. Then we had you want to research something weird, there's the whole Hale-Bopp comet thing that happened. There was like a whole cult of people that were like waiting for the comet to come and take them away. Yeah. It was weird. It was weird. It was a mass suicide and they all wore the same shoes. Yeah. And their little shoes were sticking out from their blankets. It was very, very strange. So yeah, weirdness. All right, Jupiter. Anybody want to guess our temperature for Jupiter? Oh, okay. Yusuf, you want to give it a guess? It's a guess. 500 what? Negative 500 Celsius. What do you think, Liam? 27,000 Celsius. All right, and after, what do you think?
4,003.
It's very specific. All right, so it's about negative 108 Celsius or negative 162 Fahrenheit. Yeah. Now, Saturn. What's our distance? Now, remember, they were giving this in kilometers, not AUs. So, you want to guess, Andrew?
Like a million kilometers.
1,000,000 kilometers. All right, and Lucas, you want to guess too?
64 trillion.
64 trillion. Okay, how about that? 1,424,600,000 kilometers. It's a very long way. All right, Uranus. How many moons does Uranus have? Anybody back there want to take a guess? Drew, you want to guess? 4. Piper? 15. 27. Lots of moons. And its axis is tilted, right? So it has rings. They aren't as obvious as Saturn's. They aren't as visible because they're not composed of the same thing, but they're at a different axis, tilted differently. All right, Neptune. How many Earth hours is one day on Neptune? Liam?
5.3.
5.3 Earth hours is a day. That's rotating really fast, right? All right, Yusuf? How many Earth hours is a day on Neptune? 15, 16 hours? So it's really, you got it, 16 hours. I think you need to go get a lottery ticket on the way home. That was impressive. All right, yeah, all right. 16 Earth hours. So Neptune is rotating very quickly. Compare that to Venus. Remember, Venus was like real slow. Caitlin?
It says 164.
That's the year length. So 16 hours of 16 Earth hours for a day. Yeah. And then a year. So it's going to take 164 Earth years for Neptune to make it around the sun. But in the meantime, it is spinning way faster than we're spinning, right?
How many Neptune days is one of its years?
You'd have to multiply.
Yeah, we did that one.
Alexa, what's 16 times 165?
16 times 165 is 2,640.
That's a lot. So solar system, here we are. Oh yeah, that was hours, not days. So I'd have to, have to do another conversion in there. So now we're all the way to here. So now we at the edge of our solar system. So remember we talked about Voyager hadn't gone interstellar past all this. So most of the objects in the Kuiper belt lie in a donut-shaped region close to the elliptic plane that we have going here. And it's called an Oort cloud. That's your comets and this other kind of stuff that kind of circle around, a little nebulous, but they're there. All right, so that's the whole solar system, right? From the sun all the way out. Now, how do we get these planets? So nebular theory. Okay, remember these are theories. What's a theory? A theory is just say it. What is it? Say. Theory says what? An explanation. What's a law? I mean, why? Sorry, theories. Why? Yeah. What? A law tells what happens in fact. A theory tells why it happens in explanation. There you go. So your nebular theory. Okay, so the idea is that you've got a rotating cloud. And what's in the cloud, Xander?
and gas.
Dust and gas and all this mess. Okay, and it's spinning around. All right. And then what do you call this large, thick cloud that's capable of forming a planetary system? Jordan?
Solar nebula.
Yeah, okay, but also, yep, we get this. Okay, awesome. Y'all are so excited over here. Oh my goodness. So yes, you have your solar nebula. All right, now, what do you call the disk that forms? All right, let's do Lucas.
2 brownie points on the screen says a large stink cloud of dust.
Oh yeah, it does.
A large stink cloud of dust.
It does. It says thing in there.
G.
Oh, how funny. That's weird that it's wrong. Okay, good. You caught it. There's 2. All right, so what do you call the disc? The rotating disc. Okay, Yusuf. There you go. Yes. Okay, your protoplanetary disk. What's proto mean? What's it mean, Bailey? I mean, Piper, sorry.
Like folks.
Yeah, like first. Yeah, what's another word that uses proto, Jordan?
Prototype.
Prototype's the first one that comes to mind. Yeah, okay, so prototype meaning like, yeah, it's a prototype would be like, you know, what's a prototype? Can you explain what a prototype is, Jordan?
It's like the first version of something.
Yes.
It's possible to make.
Yes, very good. So it's like the first thing. It's the model thing. If you're making a product, you know, and you want somebody to market, you'll make one and you'll show this is my prototype. All right. So then, what do you call the asteroid-like bodies that are eventually going to smush together, Colin? Yep, these are planetesimals, so they're like big rocky things, right? And they're starting to come together. And then when you start adding mass with them all colliding together, Liam?
Accretion.
Yeah, accretion. Okay, that's a good one. That's a good word. Accretion. All right, and then what is the product of accretion of planetesimals to form this moon-sized planet? What's that, Ridley? Okay, your protoplanet. There's proto again, right? There it is again. So you have a protoplanet. So you've got this big cloud of dust, comes together and spins around. Anybody ever done the thing where you sit in an office chair and you spin around and then you tuck your legs and arms in and you spin faster and faster? This is the same, these are the same forces that are. Oh yeah, tire swing, you can do it too. You can lean out and tuck in.
I learned it before, right?
Ah, I bet he does, right? That sounds fun. I bet. So your composition and your size of your planet. So your terrestrial planets are pretty small, right? And they're rocky. And then your gas giants have low densities and they're further out. So let's talk about energy from the sun briefly. Okay, what is the process that given the energy that's producing the energy in the sun? James, you haven't answered yet. What's going on with the hydrogen and helium? You know it. Yeah, fusion. You got it. All right. So you've got hydrogen and helium. Where is hydrogen located on the periodic table? Yusuf? It's the first. And right. And where's helium located? Do you know? Yeah, well, so what number is helium? 2, right. Helium is 2. Hydrogen is 1. So what's that mean? Somebody explain to me what that has to do with fusion. Okay, Colin, you want to go?
Hydrogen only has 1 proton in its
Mhm.
nucleus. Helium is 2.
Okay, Drew? Good.
The large gravitational pull of a star will condense the hydrogen atoms so much that they have the 1 in it.
They combine and they become helium, right? And then what is it called when? Yes, and what's it called when they break apart? That's a fusion when they come together and they break apart. It's Liam?
Fission.
Fission. Good. All right, so that's what's happening in the sun. That's it's nuclear fusion. That's what's nuclear, meaning the nuclei come together. This is one of these words. I've always said I'll disown you if you get it wrong. The nucleus is the center of a cell, the center of an atom. When you're talking about atoms and atomic power, it's not nuclear. No, nuclear. I will call you out every time you say nuclear. Every time. Yeah, don't do that. I mean, lots of people get it wrong. Adults get it wrong. This was a word that George Bush could not pronounce. George W. He could not pronounce it to save his life. He said nuclear every time. And I was like, why don't his aides fix that? But no. All right. Did you have a question?
Yeah.
What?
So the two, if you combine the elements for gold, if you take fusion, then we get gold.
Oh, can you keep combining to get gold? So the heavier they get, it becomes more and more complex. So something you would probably enjoy, and I think we talk about it in chemistry a bit. We probably talk about the end of this class too, I think. But there's a particle accelerator in France at CERN, 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 and they do that. They'll create an element briefly. They'll accelerate particles so quickly that they'll combine and they'll create like something that's further out on the periodic table, but they're unstable, so they don't stay long. So it's much more, I mean, it's never really stable, but it's more stable at this size than it is with more dense, heavier, they call them heavier atoms because they have more particles, right?
Also the most expensive elements.
Yes, yeah, that's true. Yeah, the heavier, the further they are, a lot of them tend to be more expensive. And that has to do with rarity too. Like how easy are they to find and what are they good for? Like lithium's what, 3 on the periodic table, and lithium's not too expensive. We use lithium in everything, but we need it, we use it. There's some other things we don't use as much, and so they're not as important. So your sun's interior. So you've got a core, and that's where your fusion's occurring, and it's a quarter of the diameter of the whole sun. So what's the dense region of highly compressed gas? Yes, daily. Yep, and it didn't even finish. Where? Sorry. And the outer layer of the sun's interior. This is using convection currents, and it transfers energy out. Caitlin?
Convection zone.
Yeah, okay. So this is our sun. Ta-da, there it is. Now, sun has an atmosphere, kind of a weird atmosphere, but it has an atmosphere. So it consists of 3 layers. You got a photosphere, chromosphere, and a corona. When you watch the eclipse and it looks like that, you get totality. You can see the corona around the edge. And sometimes you can see the little solar flares if you've got, really good equipment or it's a really clear day. So the innermost layer of the sun's atmosphere, which is visible from the sun's surface, is okay. Oh goodness, Liam.
Photosphere.
Okay, that's our photosphere. What's photo? What's photo mean? Caitlin? Picture. Okay. What else? Colin?
Photons.
Photons. Okay. What else does it mean?
Light.
Light. Lucas got light. Okay, so photo. You'll hear photo used a lot. We'll get a little further when we get into wavelengths and stuff and wave theory later in this class. So photo has to do with light very often. So taking Caitlin's example of a picture, graph means what? Piper?
Right. So.
To write. So a photograph literally means
Picture right.
writing with light. Yeah, there you go. Writing with light, which if you were to do photographs like the old school way on film, it's exactly what you're doing, right? A little different now, but all right. So the middle layer of the sun's atmosphere, this is where your temperature increases. Ridley. There you go. Chromosphere. Okay, chromo. That's an interesting one. Does anybody know what chrome or chromo? Do you know, Piper?
Metal.
Metal. There is a metal chrome. Yeah. Interestingly, chromo tends to deal with light. I mean, not light, color. So you may see that root come up. Remember when we did, if you did chemistry with me, you did chromatography, where we we took an ink and then we let it absorb fluid and it went up the strip, and you could see the different pigments split out. In biology, we did it with leaves off of plants, because you can actually split the pigments up, and chlorophyll is the pigment in plants that, is used for their energy production, right? So we found leaves like Loropetalum. You probably see them everywhere. I have them too. They're the little tiny bushes. They have little tiny leaves, and the leaves are purple, and they produce those like hot pink little fringy flowers. They're real common around here. We were able to take those purple leaves, crush them up, and do chromatography and split the pigments up. And you could see that it still had chlorophyll in it. You could see the green line, even though you couldn't see it with your bare eyes. When we let it move up the paper and divided those pigments up, we could see it. It was cool. Yeah, question? Oh, you want the next one? The outermost layer of the sun's atmosphere is what, Yusuf? There you go. That's our corona. All right, so this is what you see during the eclipse. And then what's the stream of electrically charged particles that stream outward from the corona into the solar system? Ridley? Yes, okay, solar winds. Yep, very good. Very cool. So what are some features of the atmosphere? All right, so features of the sun's atmosphere: sunspots, prominences, and solar flares. So the areas of gas in the photosphere that are cooler, what are these, Emily? These are our sunspots. Okay, they're cooler. If you look, oh, did you find a brownie point? Where is it?
This is solar phase.
Oh, yeah, it does. Very good. Y'all got 3 this time. You're doing good. So, sunspots. See the darker spots? These are the cooler spots. Cooler, kind of that's a very relative term. I mean, we're talking about the surface of the sun. Yeah, they're not as hot as the ones next to them, but they're still screaming hot, right? All right, huge loops of glass. Yeah, there you go, less hot. All right. So what are these huge loops that erupt from the sunspot regions? Oh boy. All right, Asher. These are our prominences. Sorry, these are our prominences. The flares are the release of energy. So we talked last week about climate and whatnot, and we discussed how there was the competing argument for climate change that involved solar flares. It's because it's these sudden releases of energy. They're like shooting out, and they're super hot, obviously. And they do that. Radiation does reach us. So here is this is cool. This kind of shows you what's going on in the sun. Click. Can we play? There we go. And it's a short one, but it's pretty neat. This is your fusion in the sun. Oh, wow. Okay, just crashed on me. Still up there, right? Okay. Hello. That was bizarre. Let's try that again. Here we go.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take 2 hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
You get 2 atoms to fuse. 2 protons have the same charge, they're both positively charged. They want to repel each other.
Guys, yeah.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse. And that's very, very rare.
To force protons together takes immense amounts of heat and pressure generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second, every day, about 5 million tons of stuff is being converted to energy. It's amazing.
So we got law of conservation of mass there, right? And mass can convert to energy, which is something we talk about a little bit in this class. But you have to, like, if you have mass, it doesn't disappear. Goldfish? They mass? Oh, it turns into energy. Yes, chemical energy. So have you ever taken magnets that and you turn them so they repel and you try and push them together and it's like impossible, right? They're doing like this with your hands and you're fighting them, right? That's the same thing that is occurring with these protons that are both positively charged, because positive charges are attracted to what? Negative charges. So you're trying to push 2 positively charged things together. So that's not easy. Colin?
The guy who did the voiceover in that video sounds exactly like Michael.
I was about to ask you. Recognize the voice was my next question. And it was Mike Rowe. Very good. Yes. Who's Mike Rowe? You know?
A dude who does
A dude.
the Dirty Jobs guy.
Ah, Dirty Jobs. Yes. Okay. So he did Dirty Jobs. He also has an entire organization called MicroWorks. And he is really big on supporting trade and skilled jobs versus like 4-year college degree, go be a bartender. You know, like he's big on learn to be a plumber, learn to be an electrician. And his show Dirty Jobs, if you've never seen it, you can probably see some old episodes on YouTube. But he did jobs that you don't even think about being jobs, like going underground and cleaning out sewer systems or getting inside of cement mixers to clean the inside of them. There's all kinds of things that people do that you never even think about being a job. And he gave a chance to kind of feature those people and be like, look, this is cool. People do this. This is pretty neat. We saw you, Mike. All right. So what is the distance that light travels in a vacuum in a year? What's it called? Caitlin.
Hold on.
In a vacuum, light travels a year. Shh, no, wait, let her in. Let her look. You asked earlier about, yeah, I was gonna say, you asked earlier about a character. There you go. Light year. All right, so space is a vacuum. This is the idea, right? Space is a vacuum, and you got light traveling at 9.5 trillion kilometers. Yes. Okay, we're getting to parallax. Okay, parallax is the apparent change in position. All right. So this is kind of hard to understand. I found a good video on it though that will kind of explain this because it's tricky.
On the animal that says light you, and then it has an F to that.
Oh, actually, because it was, this is light year. It can be hyphenated, and then this dash was for the answer. So that one's actually supposed to be there. So parallax is this apparent change in position, and it's a little tricky to understand. This video kind of gives you an idea of how it works.
Have you ever traveled down a road in a car and looked at the mountains or hills in the distance?
No.
If you have, you'll probably notice that while nearby trees quickly fly past the window, the mountains move much slower, and in the far distance, the moon and the stars don't seem to move at all. As you move, objects closer to you, such as the trees, seems to shift position relative to more distant objects, like the mountains. This effect is called parallax. The size of this shift depends on the distance you travel along the road and how far away the trees are. The closer they are to the road, the bigger the shift. The same thing happens as the Earth moves around the sun. Over the course of the year, some stars appear to move a very small amount relative to other stars. Like the trees along the side of the road, these stars are just closer than those that don't seem to move. Actually, all stars are moving through space, but much more slowly than parallax, so we don't notice. Now, if we measure how much a star moves when the Earth does one complete trip around the sun, we can use this to work out this angle, called the parallax angle. If we observe a star when the Earth is at one spot in its orbit, and then wait 6 months for the Earth to move around the sun to the opposite point along its orbit and observe the star again, we can measure the parallax angle. Since we already know the distance from the Earth to the sun, we can now use this parallax angle and some trigonometry to work out exactly how far away the star is. This is really useful because it allows us to calculate the distance to nearby stars very accurately. This can then be used to check the distance measured by different methods to even more distant objects out in space.
So we use this to get an idea of how far away certain stars are. And we're actually going to be talking next week, I think. Go to the next page, about another mathematical formula that we'll use when we're determining certain things involved with motion and movement. And so if you've done any geometry at all, it will be very familiar to you. So properties of stars. Astronomers classify stars by color, size, and brightness. Color and temperature. Okay, which is hotter, which is cooler? All right, Lucas.
I found brown one.
Are you paying attention to this lesson too, though? Let's be sure. What do you have?
It says other important properties of stars include their chemical composition and mass.
Other what? Oh, stars wrong? Is that what you're saying?
It says state. Other important properties of state, but it says.
Okay. All right. Well, there's 4. These were older lessons. So, all right. So the actual question. Do you know the answer to the actual question?
Like blue is hotter.
Blue. Blue is hotter and red is cooler. So when you look at a candle flame or a campfire, it's the like see-through and the blue that are hotter than the red and the yellow, right? That part at the very bottom of a candle, when you're looking at like a wick burning, you know how it's like clear right there and then blue? That's your hottest part of your flame. So when we use our Bunsen burners, which we'll do at some point, you will adjust the flame to this nice little blue cone. And if you have like yellow and red stuff flipping around everywhere, it's not what you want. You want it kind of like your gas burner on your stove would be, nice and condensed there. So brightness, there are two ways that we describe brightness, how bright it appears and how bright it really is. Emily, what are those two? Do you know?
Apparent and absolute.
There you go, apparent and absolute. So apparent is how bright it appears, and absolute is how bright it really is. So this one's going to involve some of your astrophysics. You know, how bright is it really versus how bright does it look? So size and mass are estimated using temperature and brightness. So what elements in the star absorb different wavelengths of light that can be used to identify elements? What do I want here, Sander? Absorption. Okay, absorption lines. So these are elements in the star that can be used to identify the elements. So it's like sort of like when you get into chromatography. Basically, we know what they're made of because we can see the color when with certain equipment. So most stars make up is similar to the sun with hydrogen and helium, and you're like 96-99% of the mass. Okay. Yes, Liam.
I found another graph.
Where?
Right here it says the HR diagrams are used to estimate the stars and their distance, but it's like and without the D.
Oh yeah, it's right here too because I copied it. There you go.
In
All
the
right.
Same line, it goes C and then A. There's no number there.
Yeah, I'm not going to worry about those too much because that's not a like a typo. That's a software conversion thing that I should catch, but I'm not worried about those as much. You guys have like 5 today. So HR diagrams. Okay, so this Hertzsprung-Russell diagram. We talked about a little in Earth Science last year, but basically it's like it takes all the stars and it puts them through. It ranks them like on a graph by brightness and size, and then you'll find most of your kind of main sequence stars in the middle of it. It's just kind of a way to categorize and see where they are, basically, in relation to one another. So you have main sequence stars, and this is, like I said, the diagonal band in your HR diagram. And then you have giants and dwarfs. So in the top right of your HR diagram, you have the very bright ones. And what are the very bright ones called, Ridley? Okay, supergiant. Excellent. And then below the supergiant, the smaller, fainter ones are, Xander?
Giants.
There you go. And then what do we call the remains of a medium mass star, Asher?
Dwarfs.
There you go. White dwarfs, to be specific. And I lost it there. All right, so here we go. This is a cool one, if it will play. So here's your HR diagram, and kind of the reason is there, the purpose.
When looking up at the night sky, you can be forgiven for thinking that all the stars look similar, but each one has its own unique properties. From Earth, there are two easily observable and measurable set of features, brightness and fun.
A sec. Give it a second to cache a bit, because that is blurry. Usually it'll get less blurry after a second, but still
stars doesn't really show them. And for observable brightness, it's affected by another crucial factor, stellar distance. In other words, even though one star may appear dimmer than another, could actually be brighter, just further away. When astronomers realized that we should take stellar distance into account, they were able to work out the actual and true brightness of stars. The Hertzsprung-Russell HR diagram is named after the two discovering astronomers who used observational data to create a graph to classify and study the evolution of all stars. They labeled one axis of the graph with absolute magnitude, or true brightness of the star, and the other axis with color, which is linked to the temperature of the star and defines spectral type. Stars begin their lives in large, dark, cool clouds of gas and dust called nebulae. Pockets within these nebulae can begin to contract, getting smaller, denser, hotter, and brighter. These cores are known as protostars. A protostar with too little mass will be too cool and dim, and it will never become a star. And an excessively massive, hot, and bright protostar would be too unstable. But if they have just the right mass and temperature, they begin to fuse the hydrogen gas into helium, and the star is born. Each star that is formed will take its appropriate place in the main sequence of the HR diagram. While they fuse hydrogen in their cores, stars spend their life on the main sequence. Like the majority of stars, our sun is a main sequence star. But when it runs out of its fuel, hydrogen, It will evolve off the main sequence, and as the sun's hydrogen-fused core collapses, it will reignite and fuse the helium in its core into carbon and oxygen. Its surface will expand and get cooler, and the sun will turn into a red giant star. As the helium in the core is ejected, the sun will evolve into a planetary nebula, blowing off its outer layers, leaving behind a small, hot, white dwarf star that is rich in carbon and oxygen. Stars that are more massive than our sun fuse their fuel more quickly and evolve off the main sequence to become red supergiant stars. These supergiants are able to fuse even heavier elements in their cores. When they run out of all their fuel, they end their lives in a supernova, leaving behind a very hot but small neutron star or a black hole. So thanks to the work of Hepström and Russell, astronomers can now work out where a star is in its evolution if they know its true brightness and temperature.
So closest to us, one that is definitely going, hello. Yep, one that's definitely dying, that's close to us is Betelgeuse. Or Beetlejuice or Betelgeuse. It's pronounced like 10 different ways. I think Jews is the right way. No, I don't think so. They expect it will kaboom pretty soon. I'm not sure how far away. They don't know when it basically over there. They know it's going to happen because of where it is in its life, and it could supernova tomorrow, or it might be 400 years from now. But in the lifespan of a star, it's getting close. James? Yeah, it's a good ways, but you can see it at night. You can see it for sure. It might have, but I don't think so. I think because they keep getting data, and yeah, there will be you're right, there will be a gap.
That will be 200 million years before it goes.
Yeah, that's true. So how stars form. So nebula, or you're allowed a nebula or nebulae are these large clouds of gas and dust that spread out over a large volume of space. And then you have protostars. And these are formed when your nebulas contract and heat up. And then a star forms when a contracting cloud of gas and dust becomes so hot that an adult star forms. And then you get these adult stars, right? And a star's mass determines the star's place on the sequence, which you were just seeing, because that deals with all of it links together. The color, the size, the temperature, they're all related, right? So how does it die? You get this dwindling fuel supply, and it's ultimately going to lead to its death as a white dwarf, a neutron star, or a black hole. Question?
Where do I put this in order?
Stick it on the table, it's fine. Liam.
There's another brownie point.
Where now?
It says a dense remnant of a high mass star.
Oh, okay. There you go. This stuff there was some issues when it copied from the last time I used it, and I'm not even sure. I will tell you now, because it's not, because I'm calling it out, not you. But in next week's, I think it's next week's lesson, there's a little blurb about Chester cheetah and a graph, but the graph for whatever reason did not get translated into your copy. But I'll put a picture of it up in your Dropbox so you can see what I mean. But we're going to go over it in class, so you can just kind of read past it. But you'll be like, what is she talking about? And that's why it just did not translate to your copy, and the juniors got it. I don't know what happened. So we get low and medium mass stars. So cloud of gas that's, whoop, I clicked two of them by accident. So your planetary nebula is your cloud of gas that surrounds your dying star. And then you have these high mass stars that go supernova. And this is your huge collapse, your violent explosion.
There are hypernovas.
What's the dense remnant of a high mass, that's your star, that has exploded as a supernova, James? Here we go. Okay. And then, hello. There you go. And then your spinning neutron star gives off strong pulses. What's this one, Jordan?
Pulsar.
Yes, your pulsar. And then what do you have when your surface gravity is so great that even light can't escape it, Caitlin?
Black hole.
There's your black hole. Okay. These are funky. Like, we'd love to, we understand them pretty well, but not entirely. So that's why there's like all these sci-fi movies that cover them, because they're so darn interesting. Oh.
to make a star is hydrogen, gravity, and time.
Gravity pulls the dust and gas
Okay, again.
into a giant swirling vortex. Well,
Gravity brings matter together. And when you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up.
Hold on, let me give it 1 second, see if it'll. It's cached to here, so it should stop doing that. But anyway, lagging a bit. Here we go.
hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center.
That really shows you how violent the process of star formation is. These jets are many light years across. Something is literally accelerating material very fast across unimaginable distances.
Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 billion degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born.
Oh, pretty cute. Little star. Started born. Let go. All right, so stars are sometimes in systems. So you can have a group of 2 or more stars that are held together by gravity. Okay, so astronomers have determined that more than half of all stars are members of star systems. So what do you call 2 stars? A system with 2 stars. Chloe? A binary system. Now these you can actually see if you're outside long enough. Hold on, if you're outside long enough and your eyes have adjusted so you don't have any like indoor light. Like when I went out to watch the Starlink the other night, I had been looking at stuff up close over here on the counter. When I got out there, my husband's like, there it is. I'm going, I can't see it yet. Wait, like my eyes had to adjust. You spend a lot of time outside and it get to a night where it's really clear and there's no noise pollution. I mean, no light pollution. You can see the binary stars because they look like they kind of twinkle back and forth like this. Sometimes you can see them. It's really, really neat. I swear I saw one night. I can't be positive. I didn't have anything with me to confirm it, but it really looks like kind of going back and forth. What you got?
I think I found another.
I'm sure where.
So here it says life cycle of stars, and it's 26.3.
Mm-hmm.
But here's this group of stars, and it only has little Roman numeral, not the numbers.
Yeah, that's what I'm not gonna worry too much about the Roman numeral stuff because it kept getting. That's formatting and it like takes over sometimes, and I should catch it, but I'm not too overly. Oh, that's binary. I need to click that one. Not too overly worried about it. What did you find?
Suggestion.
Well,
how about from now on, if you find a brownie point, use a hand in a fist, just so we can tell.
I'm gonna forget that. My brain's not that good. I will forget it. All right. So there are 3 basic kinds of clusters. You got open associations and globular clusters. So you've got an open cluster. This is disorganized, few thousand stars spread out. What's the next one, Piper? There you go. Association clusters, they're together. And then Caitlin? The globular ones. These are like just kind of a group hanging out. These are like the old men in a nursing home. You want to know something? Okay, so my dad's in an assisted living facility, and the doctor, she calls every time she visits. She's great. But she said they have a new activities coordinator who's a young girl, like in her 20s. This woman apparently started bingo 15 minutes early. You can't do that to old people. She said there were all these old ladies that she was going to go see, like stop in and see one or two of them. And she knew she had time because she knows, the doctor knows, bingo starts at 10:30 and she has to catch them before bingo. And these ladies were like coming down after seeing her, and bingo had already started. And they're like, are we late? Like coming in with their walkers because they live for bingo. And like this lady started early. And the doctor was like, no, I had to tell him, look, this girl jacked up the whole day. I'm sorry, because threw them for the rest of the day. Their whole schedule screwed up now because bingo started 15 minutes early. You just can't do that. It doesn't work, man. It doesn't work. So galaxies. So a group of stars, star system, that I catch that one. Star clusters, I know that's there. Dust and gas bound together by gravity. This is, yeah, these are galaxies. All right, we have different kinds of galaxies. We have different shapes. So what's the one with the bulge at the center, arms extending outwards? Ridley. There you go. Okay, so you have a spiral galaxy. And then what's like a pinwheel? And then what's the one with the bar at the center and arms extending outward on either side? Jordan?
Barred spiral.
Here's your barred spiral. Okay, and what's this? What's the one that's spherical or oval? Caitlin?
Elliptical.
There you go. Very good. Colin, what's the disorganized one?
Irregular.
Irregular. And what's this one? What is a barred spiral? What's the one that we know about? Piper?
The Milky Way
Yep,
galaxy.
we are in a barred spiral. Okay, so the Milky Way, if you go somewhere where it's really clear, no light pollution, you can see it. You can actually see like the streak through the sky. It's very, very cool. Yusuf?
We're in it.
Well, because we're in it, but we're also, it's around us because we're in it, right? So we can look out, like we're in the house, right? But we can see the trees.
Earth is on one of the arms, and
Mhm.
if it's really clear at night,
Yes.
in a certain place you can see the bar.
Yep, it's really neat. It looks like a streak of, it's a brighter because all the little stars are in it, and it's a brighter streak. Yeah, milky. It's really kind of neat. Yes.
I think this, I'm not sure if this one is brownie
Oh
point.
Lord, what?
It says spiral, bar spiral, elliptical, and irregular. It's supposed to be a comma after the elliptical.
Actually, that is called an Oxford comma. If it's put there, my preference is to use an Oxford comma, but it's no longer required. It's one of those weird rules. I like Oxford comma. There are jokes about it where it's like, no, because it's still correct. So if you have a series of things in a row, I like eggs, toast, and orange juice. Eggs, comma, toast, comma, and orange juice, or eggs, comma, toast, and orange juice. Either is appropriate. The Oxford comma is the one that comes before the and. The difference is if you don't use the Oxford comma, people could think you like eggs and then toast and orange juice. Right? So, right. And then you have to put commas in, what's the one? The one about the panda eats, shoots, and leaves. That's where commas matter. Because if you say the panda eats, shoots, and leaves, that means it eats, shoots, and leaves, right? It eats the shoots and the leaves. But if you say the panda eats, comma, shoots, comma, and leaves, that means it eats, shoots, and leaves, right? So commas matter, right? So it's this like gangster panda, right? I know. So what is the enormously bright center of a distant young galaxy? What's this one? Do we know? Okay, Xander. Quasar. Yep. Okay, so that's your bright center. And we can use Hubble's law, which we very briefly talked about, but it explains how the universe is expanding. And it is very, very similar to Doppler effect, which we will go over a lot this year. It's pretty much the same principle. It's using wavelength and how we perceive wavelength, and like one is light and one is sound, but it's the same thing. We can tell that that our universe is expanding from a central point. We can tell our solar system is expanding from a central point by checking the wavelength of stars. It will change as it gets further from us. So it's really interesting. Yes.
It says, it's a black point. It says, galaxy is moving away from Earth in proportion to its distance. It doesn't say is in proportion or is proportional. It just says
Okay. Okay. One thing I want y'all to do, brownie points are good, but don't miss the lesson because you're paying attention to brownie points. Like you have to catch the lesson. That's what matters more than catching a million little typos that don't get caught. Because I don't know why there were so many in these first couple of lessons, but there were a fair amount. And I tried to catch them when I go back over it, but I can see somebody else's mistake like this, but my own I read right over every time. So yeah, Alex should proofread everything. So the speed at which a galaxy is moving away is what, Jordan?
Like the speed.
Mm-hmm. Do you know? Not sure?
Okay.
The
speed at which galaxy is
moving away from Earth is in proportion.
Okay.
Yes. Okay. Yes. There you go. Okay. So that's Hubble's law. Right. All right. And redshift is light shifted towards red wavelength. And then there's blue shift where light is shifted towards blue wavelength. So when you see redshift in the spectra of a galaxy, you can tell that it is expanding. And when you look at the electromagnetic spectrum and you check the different wavelengths of different colors of light, it makes more sense. And we will go over it kind of later this year. We'll get more into that whole wave theory thing, but it makes a lot of sense once you see it.
And if a star's apparent brightness,
Mhm.
not its absolute brightness, but if its apparent brightness is red, that means it's moving away from us.
Right.
And
Mhm.
then fluid's coming towards us. The wavelengths are compressed.
Or it's closer. Yes. Right. All right. So here's our Big Bang theory. And again, we said a theory tells why an explanation. Okay. So this is a theory. All right. Oh boy. All right. So astronomers theorize that the universe came into being at a single moment called Liam.
There's a brownie.
Oh God. Okay. What?
It says into a single moment and event.
Oh yeah. Okay. Good.
It's called the Big Bang.
That's the answer I'm looking for. Okay. Big Bang. All right. There we go. So the theory that the universe was created 1 billion years ago is the Big Bang Theory, duh. And yes, there's a TV show called Big Bang Theory, right? I know, yeah. So it's the idea that it was created from a massive explosion. Now, again, you can use Hubble's law to prove that it is expanding, right? So it expanded, slows down, continues to expand. So evidence is the existence of what?
Cosmic microwave background radiation.
Yes. Okay. That's a big one. This is actually really interesting. So this is one of those ones that like they found it when they weren't really looking for it. And they're like, whoa, what is that? Right. Some they were looking for other types of data and they picked up this data.
13.7
13.7. What's 13.7? Billion years old. There you go. There's our universe. 13.7 billion years old. Okay. So, and it continues to expand. So dark matter. All right. This is where we get weird. Dark matter does not give off radiation. So what is this? All right. So here's another one for you. Got lots of these. Drew, did you have a question before I play it?
No, it's a statement. So
Oh.
recently scientists discovered that there's a planet orbiting nothing, it's just spinning in circles.
Hmm.
And what a lot of people theorize is that it might be a star completely composed of dark matter.
Ooh. Okay.
That'll be completely right.
That is.
So this is
Instead of satellite.
so this is one last bit on Hubble, and then we are gonna talk about dark matter because it's interesting.
Since the late 1920s, everything we know about how our universe works has been turned upside down.
It's important to realize how much our picture of the universe has changed in the last century. At the beginning of the 20th century, the conventional wisdom in science was that the universe was static and eternal.
In 1929, that all changed. At the Mount Wilson Observatory above Los Angeles, astronomer Edwin Hubble discovered galaxies aren't stuck in one place. Not only are they moving, but they're flying away from Earth at incredible speed. This was the first real evidence of the Big Bang.
galaxies on average are moving away from us, and stranger still, those that were twice as far away were moving twice as fast. And those that were 3 times as far away were moving 3 times as fast, and so on. Everything was moving away from us.
It became known as Hubble's Law. His discovery is still the starting point for exploration of the Big Bang.
What Hubble convincingly demonstrated by seeing the motion of those galaxies is that the universe is expanding.
Theoretically, an expanding universe must have started from a single point. By measuring how fast the universe is expanding, astronomers calculated backwards and figured out when it burst into life.
People ask the question, how do you know that the universe is 13.7 billion years old? I mean, smarty pants, you weren't there 13.7 billion years ago. Well, when you watch television on videotape, you hit the stop button when you see an explosion. And you can run it backwards and see when it actually took place. The same thing takes place with cosmology. We can run the videotape backwards and then calculate when it all came from a cosmic explosion.
Just rewind. It's that easy. You don't need to go to college for 4 years or whatever, and then get a PhD for 3 years after that, 4 years or however long. You just, rewind.
Just rewind on the whole universe.
Talk about simplifying.
How many of the smartest people in the world actually went to college?
Depends on how you categorize. I think smart and is different than learned. And depends. There are probably some super smart people who are uneducated, and there are definitely educated people who aren't that smart, because all you got to do is look at politics and media and you'll see that. So anyway, all right. So matter that does not give off radiation is, Jordan?
Dark matter.
Okay, dark matter. All right, this is some bizarre business here. So now we gotta think a little abstractly here. So it cannot be seen, but its presence can be detected by observing its gravitational effects on things you can see. So here's where we have to start considering the hypothesis that's involved in astrophysics, particle theory, and quantum mechanics. This is way above my pay grade, but it's fascinating. If you like math and you like theory, this is the way to go. This is all about it. So this steps, like I said, a little out of the range. So there's a couple of videos here because it's much easier to visualize with these than an explanation. So first one's going to tell you what is dark matter.
Have you ever had the feeling that there's something bigger out there, something you can't see? Well, there is. It's called dark matter. Dark matter is spread throughout space, engulfing the Milky Way and all other galaxies. It's 4 times more common in the universe than visible matter, yet we've never seen or directly observed it. So how do we know it's there? Because of gravity. The galaxy is like a giant merry-go-round that all the stars are riding. In order to stay on, each star has to hold on tight. That's where gravity comes in. Otherwise, it'll fly off into space. The problem is, the force of gravity from all the stars we can see isn't strong enough to hold galaxies together. All the stars should be flying off the edge of the merry-go-round, but they're not. It's as if some invisible rope is helping them hold on. Physicists believe that rope is the gravitational force from stuff we can't see, hence dark matter. And how do we know the speeds of stars in distant galaxies? The Doppler effect, which is why a police siren shifts to a lower pitch as the car passes, also works for light. That's how radar catches you speeding, and how astronomers measure the rotation of galaxies. So, we use what we can see to tell us about what we can't.
Okay, now you have an idea what it is. So in the next one,
Have you ever had the feeling that
go.
there's something bigger out
I love
there,
how it does
something you
that
can't
just
see?
automatically. All right,
Whoa.
this is interesting. Now you'll see.
One of the most amazing things about atoms is that they are mainly empty space. If an atom were as wide as your arm span, then the electrons would all be whizzing about inside the volume enclosed by your fingertips. Meanwhile, the nucleus would be sitting in the center, and its diameter would be smaller than the width of a single human hair. So all of the atoms that make up you and me and all the seemingly solid things in the universe are mostly empty space. Now, this is incredible, but what is even more mind-boggling is that empty space is not truly empty. I know because I've seen it. This is a simulation by Professor Derek Lineweber at the University of Adelaide. It was made using a supercomputer to crunch the calculations of quantum chromodynamics. Now that is the theory of fundamental particles called quarks, the building blocks of protons and neutrons, and how they interact with each other through gluons.
What you're looking at here is the energy density of the gluon field fluctuations. Where the little red spots come out, the energy density is very high and it fades down through the colors. So in the lowest energy field fluctuations are not rendering these animations, so we can actually see into it.
And what we see is a bubbling soup of quantum field fluctuations that come and go incredibly quickly. The frame rate of this simulation is 1 million billion frames per second. Now that is truly high speed. The dimensions of this box are absolutely tiny. They are millionths of a billionth of a meter, roughly enough space to stick 2 protons. But there are no protons here. This is a simulation of the vacuum on its own, what we normally think of as empty space.
Empty space is actually full of these quark and gluon field fluctuations. And on average, it is possible to annihilate a quark from empty space because it's not empty.
That just sounds like the most ridiculous idea that you're going to have empty space and it stuff.
Now, it seems counterintuitive that the vacuum at its lowest energy state should contain all of this stuff. But in fact, to clear out the fluctuations and create a truly empty vacuum would require a lot of energy.
The empty vacuum actually costs an enormous amount of energy to create. Discovered that it's actually unstable, that any sort of perturbation push that empty vacuum into something where the vacuum is actually full of quantum fluctuations.
Well, this may not be as strange as it first appears. I mean, consider a permanent magnet. It has a magnetic field around it at low energy, at room temperature. And that's because the individual little magnetic moments of all the atoms inside are lined up. But if you were to heat it up, you would give thermal energy to all those particles, and at a certain point, called the Curie temperature, they would be so randomly aligned that there would no longer be an overall magnetic field. So it actually takes energy to get rid of the permanent magnetic field. And this is just like the quantum vacuum. And understanding how the quantum vacuum fluctuations work gives us a sense of what the fundamental particles do. Like, where are you most likely to find a quark?
And it turns out the quark likes to sit on top of those lumps. Now those lumps come into and out of existence fairly quickly, and so we like to think of the quarks hopping from one lump over to the next lump as it appears, and then on to another one. I like to think of it as a hiker trying to cross a stream that's running around. Every now and then a stone pops up as the water's swirling around it, so you put your foot there and you look for the next spot. If you go quickly enough, you might not get your feet wet. So I think quarks are very much doing, well, we know quarks are very much doing the same thing.
So while it is true that you and I and all of the other atoms in the universe are mostly empty space, it is also true that empty space isn't truly empty. And in fact, it is these vacuum fluctuations which are essential for our existence.
If you're not subscribed to Derek's
So that's a
channel-
weird thing to think about, okay? You got an atom, right? If you've got this field, they're gone.
One of the most amazing things about atoms.
You've got this field of electrons spinning around you that's, you know, as big as your wingspan. Then your nucleus is like the width of a hair. So you've got that's all your protons and neutrons in that tiny little spot. You've got all these electrons whizzing around in this bubble, right? Well, what are they whizzing through? Like, think about it. When you picture it, you picture a Bohr model or a Thomson model, however you picture an atom, you picture empty space, but it's not really empty. You're mostly empty, but not empty. Like, think about that. Like, think about how small even a molecule is, right? A molecule that creates a lipid or even a water molecule. You're full of that. Yeah.
I was gonna say, if you took all the space out of the Empire State Building, it would be the size of.
The size of a grain of rice. Yeah. And it's weird, but it's like, yeah, like you could crunch it down to that. Isn't that bizarre? Like it's a really weird thought when you get thinking about it.
It would still weigh as much as the Empire.
Yes, it would be extraordinarily dense. So lastly,
All the.
this one is a little yeah, so this one is
The Empire State.
so thinking outside the box, okay? Last video, and then I'll show you your review stuff, but this one's a little bizarre.
This is you, made from ordinary atoms and molecules. And this is you, if you were made out of dark matter. That's how it works, right? No? What would it be like if every particle in your body converted into a dark matter particle? And how long could you last in that state? This is what if, and here's what would happen if you were made of dark matter. Everything that we can see in the universe is a massive mashup of electrons, protons, and neutrons fused into atoms. It's what's called baryonic, or just ordinary, matter. Your body is made up of it too. But there is a lot of stuff out there that we don't see. Stuff that we call dark matter and dark energy. If you were to undergo a dark matter transformation, your existence, as you know it, would come to an end instantly. But as compensation, you'd get the ability to move through virtually anything you want.
Like a ghost.
Before we change your body composition, let's make some things clear. There's no concrete proof that dark matter exists, and we currently have no technology available to find that proof. So how can we know about dark matter in the first place? Well, if you run some cosmic calculations based on physics as we know it, it turns out that the amount of visible material in the universe doesn't add up. Here's an example. A spiral galaxy, like the one we live in, has stars at its outer edges. According to what physics says, these stars should be moving at a much slower pace compared to the ones close to the galactic center. But in reality, all stars in the galaxy seem to be orbiting its center point at almost the same speed. Scientists think that that's dark matter influencing the effects of gravity and making the stars move the way they do. Dark matter doesn't interact with ordinary matter at all. It's invisible to electromagnetic radiation and light. The only thing that makes scientists think dark matter exists is its gravitational effects on galaxies. Scientists also think that dark matter outweighs visible matter by approximately 6 to 1, making up 27% of the universe. Now, let's get back to your dark matter transformation. If you're of an average weight of, say, 70 kilograms, your body has about 7 billion atoms in it. Your atoms form molecules. Molecules form cells, and cells form vitals that you can see with your eyes, like your organs. If all of your ordinary matter atoms switched to dark matter atoms, your physical body would disintegrate. Without ordinary matter, there would be nothing to glue your atoms together anymore. But this wouldn't be the end of your story. You'd become invisible, and your body wouldn't appear as a collective whole, but your dark matter particles would still interact gravitationally. Trapped by Earth's gravity, those particles would start an endless marathon around the center of Earth's gravity, the core. They'd be circling in an elliptical orbit at the speed of 3 kilometers per second. Every 88 minutes, your dark matter would make a whole circle back to the place of your transformation. The dark matter particles that used to be you would slowly drift over time. On your first dark matter birthday, your particles would show up about a half meter from the spot where they were born. After 10 years, that distance would be half a kilometer. That's because dark matter you wouldn't be influenced by our planet's rotation. Dark matter is only affected by gravity. There would be no energy or momentum loss. You would never reform to become an ordinary matter you again. You would just keep circling around the Earth's core. Of course, nothing can turn you into a dark matter entity in real life, but that doesn't mean that there's no dark matter around you. The mathematics behind it can get somewhat complex, but scientists have estimated that the average person has 10 to the power of negative 22 kilograms of dark matter in their body at any given time. Throughout your life, approximately 1 milligram of dark matter will pass directly through you. So while technically you can never be entirely made up of dark matter, it's incredible to think about how something we don't know much about could be so close to us, even part of us. There is so much to learn about the universe and how it behaves. Maybe we would have a better grasp of it if the Earth had been born somewhere inside a globular cluster and not on the outskirts of the Milky Way galaxy. Well, that's a story for another What If.
So yeah, if you really like astrophysics and whatever, that's a good way to go. It's all theoretical physics, quantum mechanics. But when you think about it, hang on, wait a minute. Empty space isn't really empty. And then there's something else we can't see moving through us. All right, so listen. Want to make sure everybody understands. These, I'm going to show you your study topics. These are also in Dropbox in the resources folder. If you look, there's one that says unit test study topics, and you click on it, it'll say unit 2, and you click on it, and it'll say lab rats, junior lab rats, you pick yours, and the same exact thing will be there. Okay, the same image tells you what the topics are. These are going to be the topics for this particular test. Okay, be sure that you have studied them well before you start your test. Once you open it, like I said, you got 60 minutes and you're done, right? That's it. Now, it is online because Teacher Use is working. Hooray, hooray. We went through a couple of weeks where it wasn't working. It was a nightmare. So lastly, when we have a test, we don't have homework leading up to it. Sometimes there'll be a binder work question, but there's no homework leading up to it. Questions? Yes.
It's just an interesting fact. I can tell you that.
Yeah, sure. All right, so let me turn these around so you guys can come collect coins. You're good to go, and I'll see you next week after your test. What's your interesting fact?
Any number of kilograms. Kilograms is measured mass, not of weight. So not really weight.
Yeah, it's a mass measurement, but it's used because there is a universal effect of gravity on Earth. They use it for weights in metric system because they consider the universal gravitational pull to be the same. But you're correct; it is a measurement of mass, and mass and weight are not the same. Yeah, did you get yours?
I don't think it is.
Anybody thinks this is theirs?
I
Oh, yeah.
didn't.
I still have one. Somebody didn't get credit. You're gonna want to look. Yep, if you didn't get it back, James, somebody didn't get credit. James. Yeah, I don't think it's yours. You got two returned.
Please.
Yep.
Take them anyway.
He's not gonna use them.
Yuck in your shoes.
He doesn't even have that many.
Buddy. It's a good fella. No, come on. Come see my face. That's my boy. Baby boy. If you want the little cups, here they are. If you want the littles. Here. Sorry. He is fully aware of what he did. We'll do it. Yeah. He is so miserably spoiled, aren't you? You've been really. He gets excited on Tuesday mornings and then y'all are coming and he gets excited about it. He'll get something, put it in his crate and then he's more excited about it. You can tell like what day when he is. You can tell when all the time. You gotta do the same like that. The desk comes out, the room gets set up. I usually do the night before, but Tuesday morning, everything's out for the first time, you know, and you go, oh, you're coming. You know, how it's gonna come. You're welcome. Right? Right? Yeah, you're very well. Page. Find it over there. You're gonna be bad. That was bad, right? You're laughing. I just noticed it is broke. So that's a photograph. Try to copy. You go there and check that out. You see it? You timed it. You see the little pound? Oh, yeah, stop that. You hear it? The other one's to the top on the piano. Hear it? Right. You just heard it. Yeah. Yeah. You see that over there? On the other side of that little truck. You can tap that and answer that to Jordan. Yeah, I hear it. No more. Yeah. So, what do you think?
Sociology, algebra one, and literature.
Very cool. Your mom said you found your people in the theater group. I told her theater people are the most accepting humans on the planet, so long as you're off book when you're supposed to be off book, and you know you're blocking. So,
I'm
you're in tech, right? Yeah, yeah. I have a neighbor of mine used to do tech years ago. Is that fun? You enjoy it?
Yeah, we're doing 4 shows this year, and I'm working on all of them.
What are you doing?
I do hair and makeup, props, and costume.
Very cool. What shows are you doing?
Little Women, 9 to 5 the musical.
Yeah.
12th night, and then we're doing our new theater.
Very cool. Sounds good. Sounds like fun. Good. Yeah. Theater tech school. They have a good, Brown University. I have some friends that are there for theater and theater tech type stuff. And that's just a game, it's not very far. And they, one of those to the theater, you know, where they go to theater, all that goes to theater. That kind of thing. That's fun. It's cool. That's a fun one to do. Yeah. Makeup and hair. That's cool.
Yeah, I only got that for Little Women though, so it's, well, I got it for the cabaret Little Women, so it's easier stuff.
That's sweet.
Yeah, but I wanted to get it for 9 to 5, 9 to 5 has some fun, so.
Oh, I was gonna say, the hair for that's gotta be fabulous.
It's really fun.
That's good. I'm glad you got it.
Props and which I'm not really doing much.
Yeah.
Mainly what I'm gonna do is.
What about that? Sorry, props, you said.
Help the people who are building sets. And stuff, because
Right.
for the sets, basically, I told them I could use a saw and
Oh, we want you, you know how you saw. Come on in here, girl. Guys on woman. Yes. That's cool. That's very cool. Do you guys get, do you borrow a lot from other places? Like, do you do the shows where the costumes and the set kind of move from one to another?
We have a really high budget, so we buy a lot of stuff.
Oh, wow, okay.
Like our budget this year, I think was $20,000.
Oh, wow, that's great.
Yeah.
That's really
Well, last year we won 2 shows, because we did Chicago.
Oh, that's good.
And we won 2 shows, so the theater department had a lot more money this year.
That's super. What's that? Yeah, that's where that piano came from, actually. It was part of it was in a play. But it was not functional. It was like in a barn. It was a barn find, basically. And it was, supposed to be one where, like the character just sat on it or stood on it or something. So it didn't need to play. So they just painted it up and made it look good. And then afterwards they were like, well, we'll just throw it away. And my friend, whose son was, I think he was doing paper tech actually, she was like, yeah, take it apart and sell parts of it. She posted that she had that harp, and it's funny because I was looking for one at the same time. And I was like, oh my gosh, I gotta come get it. So I'd borrow a friend's truck, you know, because it's massive and heavy. Yeah. That's fun though. I'm glad you're having it. You like it? Yeah. Challenging?
I think it's a lot better because I have more of a schedule.
And it's forced on you, so you have to do it. Yeah. Well, sometimes that's, you know, that's necessary. Yeah.
Yeah, it's a lot easier to not fall.
Did they put you in it? Is it 10th grade or is it just like per class or how'd they do it?
I'm a freshman, so 15.
Oh, okay, freshman, all right.
Well, one of my classes I'm supposed to, sociology is supposed to take as like a sophomore and onward.
Right.
But I had circumstances, because I already took the class that you would be taking.
Yes.
So they put me in sociology. It was either that or, I think it was AP, American Government, and I don't want to take AP.
Yeah. Well, Cole had his first test today, so I have to hear how it went. So he tested in for Spanish, he tested into third semester Spanish, and we're all excited. We're like, oh, great, you don't have to take the 2 intro semesters. And then he's like, he tested in, but they didn't have an opening. So they said, okay, well, we'll put in this religion class, because Baylor requires the religion classes for. They're like, we'll put this in as a placeholder, but if the Spanish opens up, we'll put you in it. So the Spanish opened up, and he got in it, and then he's like, it says Monday, Tuesday, Wednesday, Thursday, and Friday. And I said, that can't be right. College classes aren't like that. It's it's Tuesday, Thursday, and Wednesday, and Wednesday, Friday, something's wrong. I was like, how long are the classes? And he said 50 minutes. I'm like, oh, it doesn't add up. Like if it's a Tuesday, Thursday class, it should be longer, right? Because it's only 2 days, not 3. So he goes the first day, they put him in third semester, accelerated. It's at 8 a.m., 5 days a week. 8 a.m. I thought it was hilarious. He doesn't think it's that hilarious, but I'm like, dude, I had 8 a.m. classes for 4 flipping years. Welcome to college. Enjoy it. We'll have a good time.
Yeah, I was taking Latin and I switched out that.
Ah!
I'm gonna get that over the summer, or I'm gonna take German online.
Oh, yeah, that's fun.
I already took German, so I kind of.
Right, so you feel like you have some idea of what's going on, so you're not totally coming out of left field.
Yeah.
Okay, let's sing a ring. Somebody didn't return the ring. Fun. Try to get them out of here a little earlier next week. It's taking everybody a year and a half to crank that machine. Gee. So that's good. Are you you working or anything? Are you just dancing?
No, I'm on the flag football team.
Wow. What are you playing? Position?
The season hasn't started yet.
Okay.
So it's October 1st.
Okay. Do you know what you've been playing?
No. They kind of like tell you.
Yeah.
So at tryouts, they kind of give everybody like a general idea.
Is it a co-ed team or is it a co-ed team or is it just girls?
No, it's just because it's no contact.
Yeah.
It's just girls.
That's fun. We used to do, there was an event once a year, and it was called Powder Puff Football. And it was a flag football game that the girls played, all the cheerleaders and then whoever else. And the boys, back in the 90s, when I guess people could laugh at it and whatever, the boys dressed as cheerleaders. And they would all like, they'd wear wigs and they'd get into cheerleader uniforms and they'd try to do all the things that the cheerleaders did. It was great fun, but I probably couldn't do it nowadays, so they would get offended by it, but it was fun. Like Jason did it. There's a picture of him in the yearbook with his grandmother's wig on. The cheerleading outfit. But it was a fun thing to do. I mean, it wasn't, nobody was picking on anybody, it was just goofiness.
I was gonna do lacrosse.
Oh,
next.
tough.
Like during winter.
Yeah.
But I kind of don't want to do that because my sister did lacrosse.
Oh, which one?
Yeah.
Uh-huh.
She did lacrosse, so it'll be a little bit more like, they know more about lacrosse.
Yeah. That's a tough sport. Those are kick butt girls that do that. Actually, there's a girl I know from church who did she did lacrosse and she got recruited to ECU, East Carolina. So she went good boy. She went to ECU for no, she field hockey. She may have been field hockey. They're so similar. I don't remember. But she's a nurse now. She's already graduated out, but she was a kick butt girl. Look at that. Yeah, you know Sky.
Vienna got scholarships for lacrosse, but she played, I think her junior year because Chattahoochee's lacrosse team wasn't the best at that time.
Yeah.
But our football team was kind of bad, but our flag football team.
Well, that's good.
Yeah.
That'll be fun. I had a lady I used to work with, and she did it was just it was contact. It was full contact football. It was crazy. And I went to watch her play once, and they played some team from a more writing this furniture. But they played some team from Florida when I went to watch. It was crazy. She was a short, really thick, stocky lady. So she was 10th event or something. The girls they played were huge. They were huge. It's like, I would be terrified to be out there with these girls. They're like "Rawr, monster women, you know? Craziness, just wild. Well, I'm glad you swung by. Is your mom out there? Or she? Oh, okay. I was just going to your mom. I'll come out and say hey, but I know your friend, so I'm glad you said anytime. I told your mom, anytime you want to stop by, we'd love to see you. Kids are like, yeah.
Hopefully next month, if we're not in Illinois, because I have another effective week.
Oh, do you? Okay,
We
wow.
have every month, we don't have.
Okay. Yeah, because I don't have the Fulton schedule lined up for this class, of course, but not the Fulton.
Crazy. We
Yeah.
start the school year early and then the end, it's the school year.
They did
Well, we
that
get
this year.
The 5-day weekends, we don't get, like, winter break is.
Oh, okay. They did that in Virginia Beach this year, and it was really weird. They never started school till after Labor Day, primarily because it's, you know, too many tourists everywhere on the roads. So they just waited, but this year they started before August was even over, and everybody was whining about it. Yeah, you're good. You're fine. Well, wait, sit down. You're good. It's just noisy. Well, I'm glad you swung by. Good to see you. Anytime. For real. You know where to find me. You can text me, whatever.
I'll probably do that.
Come on back. We'd love to have you.
Bye.
All right, bye. Tell your mama said hey. Oh, and squeeze those babies. Oh, thank you. Squeeze the babies that aren't quite babies anymore. Yeah. See you later, Sky. All right. You're welcome, Clark. Now, Awesome. No, sir. You're a good boy.